The further away the sound wave is from the speaker, the longer it has traveled. The phase has therefore shifted more relative to the initial phase of the sound wave when it was close to the speaker. The following trick will help us to freeze this phase displacement, so to speak. We can copy the speaker's output signal and paste it at the position of the lamp and the microphone. We can then add the outcome to the signal that is received by the microphone. The angle between the spinning wheels, that is, the phase difference, is now fixed. It stays as if it were frozen, even when the wave propagates. With increasing distance, the lamp is now periodically emitting bright and dim light, depending on the phase difference between the two spinning wheels. At the minimum, that is, with a phase displacement of 1/2 wavelength, the two spinning wheels are directly opposed to each other. At the maximum, that is, with a phase displaced by 1 full wavelength, they point in the same direction. The phase difference grows steadily, with the result that bright and dim light alternates at intervals of 1/2 wavelength of the sound wave. If we wave the bar up and down, we can scan the sound wave in the room, so to speak, and after long time exposure, we get a pattern of the minima and maxima of the sound wave.